Okay, now let's talk about the Perceptron Learning algorithm. The difference between the Perceptron Learning and the logistic regression is that instead of using the logistic function or sigmoid function, we're going to use this step function. So we are going to output a 1 when z is 0 or larger than 0, and we are going to output a 0 when z is a negative number, so it's less than 0. So this function is a step function, and we cannot compute the derivative of this function because it's not continuous. However, if you use that function in your learning rule, in the same learning rule that we derived for logistic regression, it works, and this is called the Perceptron Learning. So it has a good performance. The only situation with this rule is that we cannot justify mathematically where this term comes from. That's the only difference. But this is an important learning rule in terms of the history of this, because this was one of the first learning rules proposed like 60 years ago when people started working on neural networks. Another method that I would like to talk about is the Newton method. The Newton method, we can use it also for estimating the parameters of our classifier. So consider a function f of real numbers. So we'll map real numbers to real numbers, and that we want to find the optimal value of theta. Let's consider that this theta is a function of this parameter, and we want to find the point in this function where the evaluation is 0. Okay, so suppose that this f function is this curve, and we want to find the position where the evaluation is 0, this position here. So what we do is simply start in a random position. Suppose that we start in this position here, 4.5. What you do is you evaluate your theta value in the function f in the curve. So you get this value here, and then you compute the tangent line to this point in the curve. So you will get this straight line. You extend the line until crossing the x-axis in 0, and then you will have your second value of theta. So in this second value of theta, you again evaluate it in the f function, which is what we have done here. And from here, you again generate the tangent line in that point until crossing again the x-axis where y equals 0. Okay, and you keep doing that until a point where you have already found a point in the function where it crosses the y equals 0. So that rule is this one. You initialize your theta with any random number, and then you will subtract the current value of theta. You will subtract from it this number, which is the evaluation in the f function of theta, the current theta, over the evaluation of theta in the first derivative of our function, of our curve. This is very easy to compute or to derive this rule. Just observe that here we can create a triangle. Okay, theta is this value here. So if we know this value, we can compute the f of theta, which will be this side of the triangle. Okay, and we want to know this, how long this side of the triangle is. That's what we want to do, so we can subtract the original or the first theta minus this to move to the next value of theta. So we don't know this, but we can find a relationship that will allow us to compute this. So that relationship is the tangent of this angle here. The tangent of this alpha angle here will be this side, which is f of theta, over this side here. Okay, And we know that the tangent of this line will equal the derivative of this f function in this point, which is exactly the first derivative of f with this theta. So we have the tangent, so the first derivative equals this side, which is f, over this here. So we simply solve that equation for this side, and then we will have f over f prime. Now this rule here is when theta is an scalar, so it's only one number, and we need to solve this for many parameters. The only thing we need to do is to use what it is called the Hessian matrix. But here in this slide, before going to the final equation, we can talk about how we can apply this for maximization. So in the previous slide we saw how we can go down, but you can also go up. So the way that you do or you need to implement this rule for going up is simply computing here in the numerator of the rule the first derivative, and in the denominators you're going to take the second derivative of the original function. So this rule will be for maximization. Now, what I said before, here we always want to estimate many parameters. So this Newton rule for many parameters, which is called the Newton-Raphson method, consists in updating this with minus this big H, the inverse of this big H, times the gradient of the function that we want to minimize. And this H is called the Hessian matrix, and is simply the partial derivative with respect of theta I and theta j in this matrix. So this is the way you would implement Newton method, the Newton-Raphson method for linear regression, if you don't want to apply the stochastic gradient descent. And well, this is all so far about classification. In the next lecture, I'm going to talk a bit more about linear regression in a more generalized form, explaining how we can use other functions and not only polynomials for doing linear regression. And in the case of classification, I am going to talk about how you can implement classification when you have multiple classes instead of only two classes. So I hope this will be useful. Thank you, and talk to you later. Bye.